Okay, to continue with the elimination and the clearance chapter, we will talk a little bit about the clearance before we go into the hepatic clearance. If we remind ourselves with the clearance equation or equations that we usually use for total clearance, systemic clearance, or just clearance, or we said total clearance. Okay, we had so many equations that we can use according to whatever that you have available as information. One of it is K as elimination rate constant multiplied to volume distribution. And we have clearance that is equal to rate of elimination over concentration in the plasma. And we mentioned that this should be at certain time and this at certain time. And we said that because we are talking about um, total clearance, this would be elimination rate. Okay. Another one is that the clearance is the sum of all the excretion clearances plus the metabolic clearances, which is we mentioned that could be usually the hepatic if it's the metabolism is happening in the liver, and this is majorly as a renal. Okay, and we also said that the clearance would also be equal to the dose over area under the curve total. And this is what we mentioned for now when we were talking about linear kinetic or first order kinetic, and we were talking about the model of IV bolus one compartment model. Okay, so we just go from here to whatever is mentioned here. Let's see that in here we are having elimination rate constant, amount of the drug eliminated or change in the amount of the drug eliminated per unit of time that is equal to total clearance over concentration multiplied to concentration, which means that the total clearance would be the rate over concentration. If we are defining it as let's say in words, it's the a proportionality constant that describing the relationship between the substance or the drug rate of elimination as amount per unit at a given time, its corresponding concentration in appropriate fluid at that time, which is the same as this equation that we already know. Okay, another thing or another equation, as we just mentioned, it's K multiplied to VD. So it would be, and again, whatever the equation that we are using, the unit is volume per time, as we mentioned before. Okay, it's the hypothetical volume of the blood, plasma, or serum, or any other biological fluid from which the drug is totally and irreversibly removed per unit of time. And it's true because we mentioned that the elimination is irreversible loss of the drug, whatever is metabolism or excretion. And the unit is volume per time, as we mentioned, and this won't be changing, but we are just adding here that it could be presented or normalized to the body weight or the body surface area, as in pediatric. Example of that, similar to when we had in previous questions, that the dose, if you remember, equals uh, milligram per kg, right? This is normalized to the weight. Similar thing for the clearance. It's rather than volume per time, it's also per body weight or volume over time per surface area. So again, if you have the weight or surface area, you can calculate it back to the clearance that you are already know, which is volume per time as a unit for the clearance. Okay, as definitions, again, systemic or total clearance is sum of the all organ clearances that contribute to the overall elimination of the drug, which is the definition of this equation that you already know. It's the sum of all clearances or all organ clearances that involved in the elimination of the drug. When we are talking of the renal clearance, if you remember that to determine the renal clearance, if you're having the total clearance, okay, and you want the renal clearance, we mentioned before that we have fraction of excretion. This would be equal to renal clearance over total clearance, right? So our renal clearance would be equal fraction of the drug excreted multiplied to the total, okay? And again, if we are having metabolic clearance, it's metabolic over total, then it would be fraction of metabolism or the metabolized to drug over multiplied to the total clearance. And by the way, you already know this, but it's just written in different way. But you already know those kind of equations, right? So if we want to define the renal clearance as the fraction of total clearance of the drug that is removed from the body by renal excretion, it's the fraction of the total clearance that is removed from the body or from the systemic circulation by renal clearance. So that's why it's called fraction of excretion. The metabolic clearances is the fraction of total clearance of the drug that is removed from the blood by metabolism, whatever the metabolic organs that is involved or that are involved. So the fraction of the total clearance that goes through metabolism. And when we are talking about hepatic clearance, again, if the metabolism is only happening by hepatic metabolism, then if, let me write it, if the metabolism only happens in liver, then by default, the hepatic clearance would be equal to the metabolic clearance. If not, then it would be just the hepatic clearance would be part of the metabolic clearance, and this would be equal the fraction of the hepatic metabolism multiplied to the total, right? So the hepatic clearance or clearance in the hepatic, fraction of the total a clearance for a drug that is removed from the blood by hepatic metabolism. Again, those are the definition word-wise. But you already know each and every one of them if you know the equation in here and you know the equation in here, so you are fine. Okay, this exercise is just a direct calculation or substitution of numbers, so you'll be fine to determine it by yourself. So again, let's a little bit talk about the two definition or two ways to determine the clearance of the drug. We mentioned that we already can use the elimination rate constant multiplied to volume distribution or elimination rate over concentration. If we remember what is the way to determine the K, and let's say for now you know the IV bolus, we know that in one compartment model, what you know so far, that you need to have log concentration or length transformation versus time on rectilinear profile to have a linear profile. Then from this slope, you can define a K, right? So we needed the drug to be, in this case, to be following linear kinetic and one compartment model. Otherwise, the profile won't be giving me this profile. I won't be able to determine K. That's why this definition of the clearance is called model dependent or compartmental model definition, because I need to have one compartment that is specifically related to one compartment IV bolus. But when we are talking about the rate of elimination and concentration in the plasma. First of all, we need to have certain concentration measured of the plasma, and I need to determine the amount or change in the amount of the drug eliminated per unit of time. Okay, and this is what we have it as this. We have rate, if we are talking about um, what you already know, which is rate of elimination, let's say, per unit of time, and we had this, okay, on rectilinear profile. So I have different time point and different rate of elimination at different time points, right? Again, if it's linear kinetic, it will show me this profile. If it's not, it will show me different profile. But if we are talking about concentration in the plasma, okay, again, it will show me this profile if it's we are talking about one compartment linear, but it may show me different if not. So I'm taking this and I'm taking this to use it to determine the clearance according to this definition. Does this mean that I'm assuming any assumption to have this calculation? No, that's why it's called non-compartmental model or non-compartmental definition of the clearance. Or in another way, we can call it compartment independent definition of the clearance. It does not need any number of compartments to have to calculate the clearance using this equation. Okay, let's talk now about physiological definition of the clearance. We already know that we have a physiological model of the kinetic. If you remember, we had physiological model in which we said that we need to know what is going to the different organs and what is going out of different organs. We need to know the flow of the blood to that organ. We need to know what is in and what is out as concentration of the drug, and if the drug is if the organ is a drug eliminating organ, we need to know what is eliminated from that organ. For the kidney, we need to know, for example, in here, the excretion from the kidney and the metabolism from the liver. This was the definition of the physiological model, a kinetic model, and we mentioned that in the introduction chapter. If we go and try to know what I will have as definition of the clearance in the physiological model, first of all, if we are talking about, again, the clearance from certain organ, it means that I need to have certain organ, okay? As I mentioned, we have in and we have out. I need to know concentration in and concentration out, and I need to know what is going as elimination from that organ. If we consider this as organ X, can I use this model, which is again physiological model? Why we call it physiological model or definition of the clearance? Because I'm taking into consideration each and every organ alone that I'm interested in. If we want to determine the clearance of that organ, again, it's a physiological definition of the clearance, is the fraction of the blood volume containing the drug that flows through that organ and it's eliminated per unit of time. Again, the clearance of that organ should be volume with the unit of volume per time, right? So it would be the fraction of the systemic circulation that contains the drug that is eliminated from that organ per unit of time. Okay, how we can define the clearance from that organ? We need to know something that is called extraction ratio. Okay, which giving us an idea was it's extracted or eliminated from that organ. And we are talking about ratio. How we can do that? It would be equal concentration N to the organ minus concentration out over the total, which would be concentration N, right? This is extraction ratio. The majority or in most organs, the N is the concentration in artery and the out is concentration in the venous, but it's not usually right. And one exception of that is, what is the exception of the N as artery and out as veins or venous, arterial or venous? What is the exception for that that you already know? And I'm pretty sure that you already know it. But just to make sure that we are not confusing ourselves in the exam or when you do calculation about the physiological clearance, just keep it as N and out over N. This is the extraction ratio. The unit of the extraction ratio is, if you're having concentration over concentration, is unitless. We don't have unit for that ratio. Okay, so if we are talking about ratio, it means that we are talking about a fraction. The least value of it is 0. The highest value of it is 1. If the extraction ratio of certain organ is 0, it means it's non eliminating organ, right? If the extraction ratio of that organ is 1, it means it's a 100% eliminating organ, okay? So accordingly, we may have 0 to 1 values, and we have values in between. Either the organ is non-eliminating or the organ is 100% eliminating organ. And you can just think about it here. When you will have extraction ratio as 0, and when you will have it as 1 to understand whatever I'm saying. This is just the extraction ratio of certain organs. So you can have it for the kidney, you can have it for the liver, you can have it for any organ in the physiological model. So to determine the clearance of that organ, it would be equal the flow to the of the blood to that organ multiplied to the extraction ratio of that organ. So upon our knowledge so far, the flow of that organ and extraction ratio of that organ are the factors that affect the physiological clearance of that organ. Okay? Again, it could be limited by the extraction or limited by the flow. It depends. Okay? But whatever the extraction capability of that organ, it won't be higher than the maximum flow of the blood to that organ for sure. Okay? And all of whatever I mentioned is here. And don't forget is a definition. This definition of the clearance is called physiological definition of the clearance or physiological model. As I mentioned, the ratio, extraction ratio of the drug, which is usually used to categorize the drug and the hepatic clearance range from 1, the range of the extraction ratio from 0 to 1. We said this is non-eliminating and this is 100% eliminating. If it's a point, if it's 0 to 0.3, let me just write it here, 1 second. So if it's 0 to 0.3, we call it low extraction ratio drug. It could be 0.3 to 0.7 intermediate extraction ratio drug or 0.7 to 1 or higher than 0.7 to be high extraction ratio drug. And we have different examples as we study the kinetic of the drug and the elimination of the drug. We can determine if they are high, low, or intermediate extraction ratio drug, and those are example of the hepatic extraction of different drug. Okay. Let's talk a little bit about the hepatic clearance using the physiological approach. And as I mentioned, in the organ clearance, we usually take into consideration renal for the excretion or hepatic for the metabolism. And we will mention that in the absence of the protein binding, as this would be the another thing that we need to take into consideration. So far, we will study the hepatic clearance in absence of protein binding. Okay, the intrinsic clearance, again, one of the clearances that we will use is called the intrinsic clearance of the hepatic, which means if we go back to this, I mentioned that we could have a flow as factor and extraction ratio of the drug, okay? And this would be the maximum that can the organ reach if the clearance is measured without any, if we consider that the extraction is extremely good, this would be the maximum that we can reach as it's the maximum flow to that organ. So if we consider that the inherent ability of certain organ to eliminate or metabolize, if we are talking about the liver, metabolize that drug without any restriction of the flow, which means let's consider this is the room. Okay, let me just draw it another way. Okay, let's have one room, which is, let's say, your classroom, and we have this door, okay, of the that room, and we have, let's say, 100 seats here for the student, but I'm giving the student only 5 minutes to go inside the room. It means that once the 5 minutes are done, that the seats would be, we can't let any students to enter the room, and whatever the seats are occupied, they are occupied. It could be not all of the seats are occupied, right? So this would be limited by the flow of the student to that room, right? So we will consider this similar to the flow to that organ compared to the ability of the that organ to have, let's say, if the seats are the enzymes of the metabolism, to do metabolism. So let's say we have, let's say, 15 seats only occupied. So the ability of that organ to, or the extraction ability or extraction ratio. The ability is the simulation of the extraction of the drug. The ability of students to fill different seats here was affected by the how much is or how many students are going inside that room. Okay, so this extraction ratio was affected by the flow. Okay, but let me just forget about the intrinsic clearance for now. But if this whole wall one of the class was removed, okay, so it was widely open and we didn't have any restriction of the flow of the student to the room. It means that all 100 seats will be filled, okay? And any students more than 100 seats, or let's say more than 100 students, will leave at the end. Why? Because none of the seats are non-occupied anymore. So those 100 seats are considered the intrinsic intrinsic or inherent ability to this room to be filled, which is the maximum way. If we consider it as enzyme, okay, or metabolizing enzyme inside that organ, if we are talking about hepatic metabolism. So it's the intrinsic ability of that organ, the liver, to metabolize 100, let's say, or using 100 enzymes, because we are removing any restriction related to the flow. Again, in the usual case, we are having both of those factors affecting the clearance, but when we are talking about intrinsic clearance, it's the total ability of the liver or any organ to metabolize the drug in the absence of the flow limitation. We call it intrinsic clearance. Okay, so if we are talking about clearance of the hepatic in absence of the protein binding, it will be equal to the flow multiplied to the extraction ratio, which could be, if we are having it in terms of intrinsic clearance, equals intrinsic clearance over the flow plus the intrinsic clearance of that organ. And for sure, if we are talking about metabolizing enzyme for certain drug, so or the intrinsic ability to metabolize certain drugs, so that's why the intrinsic clearance is related to certain drug, because the metabolism of drug A would be different than metabolism of drug B, and the intrinsic clearance of drug A would be different than intrinsic clearance of drug C, right? So let's talk about two main let's say two different extreme of the hepatic clearance, or two different cases that we are talking about. We will either have it as intrinsic clearance for the or hepatic clearance for the low extraction ratio drug, and or hepatic clearance for high extraction ratio drug. Let's start with the low extraction ratio drug. Okay, if we are talking about low extraction ratio drug, it means that the flow of the hepatic organ or the liver would be larger than the intrinsic clearance of the hepatic, right? If we write the equation, which means that would be the intrinsic clearance is the rate limiting step, okay? 1 second. Okay, so this is the rate limiting step because it's the slowest process that we have. Okay, let's write the equation that we already mentioned, which is Q multiplied to the intrinsic over the intrinsic plus Q. Okay, so if the, and for sure this is the hepatic and this is the hepatic intrinsic clearance. So if we are talking about the intrinsic clearance that is very small compared to the flow, it means, okay, it means that we can neglect it here, and if so, then we will have S goes with this, and then at the end, the the hepatic clearance would be estimated to be equal to the intrinsic clearance of that, of the hepatic intrinsic clearance of that drug. This is if we are talking about low extraction ratio drug. So the intrinsic clearance of, of that drug is very low. And you can just, without doing the whole thing, knowing that the rate limiting step is there, so is the intrinsic clearance. So the total hepatic clearance would be equal to the intrinsic clearance of that drug. If we are talking about the again hepatic clearance in case of high extraction ratio drug, which means that the flow of the hepatic is very low compared to the intrinsic clearance of that drug, right? This means that this is the slowest process or the slowest rate in this case, and it's the rate limiting step. Okay, which means that at the end the hepatic clearance would be equal or estimated to be almost equal to the hepatic clearance. And let's see how this happens. If the clearance hepatic equals the flow hepatic multiplied to the intrinsic clearance over the intrinsic clearance hepatic, okay? If the hepatic flow is very low, okay, then we can ignore it or neglect it because it's very low. So accordingly, this would strike out the clearance, intrinsic clearance at both sides, and then the um, hepatic clearance would be estimated to be equal the hepatic flow. And again, as I mentioned, the rate limiting step would at the end determine or control the total hepatic clearance in this case. Okay, and I will stop at this point to continue with